on Sicily's breathtaking eastern coast. The mighty silhouette of Mount Etna rises more than 3,300 meters above the Mediterranean. See a titan whose eruptions have both terrified and fascinated people for millennia. But today, one of its most dramatic risks isn't explosive lava or volcanic ash. Instead, it's a slow, steady movement. The entire southeastern flank of Mount Etna is sliding toward the Ionian Sea, and it's happening faster than scientists ever expected. Let's unravel this remarkable story of one of Earth's most closely watched volcanic hazards, a tale of geological forces, scientific discovery, and what the future could hold for millions living in its shadow. Mount Etna is no ordinary volcano. Perched at the boundary where the African plate dives underneath the Eurasian plate, Etna has grown from layers and layers of erupted lava, building a complex system of vents, craters, and shifting ridges. The very process that makes it so fertile, productive, and beautiful also makes it unstable. Unlike volcanoes, anchored in hard bedrock, much of Etna rises on shifting marine sediments, soft, ancient remnants of a lost sea. That difference is key. As Etna's eruptions inflate its flanks, gravity tugs relentlessly at the mountain slopes. Picture stacking heavy books, not on a sturdy table, but on a mattress. With every eruption, every deposit of new ash and lava, the southeastern flank grows taller, heavier, and steeper until the mountain's very foundation has no choice but to slide. Scientists first noticed Etna's instability from land. The Valle del Bove, a massive horseshoe-shaped scar on the volcano's east face, was carved out thousands of years ago by a catastrophic collapse. But clues went deeper. Underwater surveys mapped enormous debris fields on the seafloor of ancient landslides, where entire chunks of the mountain had once plummeted into the Ionian Sea. Geologists began to realize these weren't scattered accidents, but part of a pattern. Etna has failed before, and it could fail again. In the 21st century, the story took a new turn with technology. High-precision GPS networks, radar satellites, and ocean floor transponders began to track Etna's movements down to the millimeter. In a dramatic episode during 2017, instruments registered a 4-centimeter slip in less than 2 weeks. No eruption, no earthquake. Just the mountain's base moving as a single, massive block. Not magma pressure, but gravity itself was driving this slow-motion landslide. Etna's underwater footsum, 12 kilometers from shore, was sliding most rapidly, with movement gradually decreasing toward the summit. This gravity-driven instability means that, over the past decade, the entire southeast face of Etna has been sliding several centimeters per year. Data now show that the greatest stress is not beneath the summit, but at the submerged flanks, where soft marine layers lubricate the mountain's slide, and this realization carries consequences. If movement was caused mainly by magma and eruptions, the biggest shifts would occur near the volcano's center. Instead, it's as if the whole southeastern face is a rug slowly sliding off a table, held back only by friction and luck. The scientific consensus has become clearer. Etna is more vulnerable to catastrophic collapse, sudden massive landslide, than anyone imagined just a few decades ago. But what would that collapse mean? Let's explore the scenarios. In the worst case, a huge mass of volcanic rock, hundreds of billions of tons, could break off suddenly and crash into the sea. The impact would unleash vast energy, generating a local tsunami that could reach eastern Sicily, Calabria, and even distant Mediterranean shores in minutes. Coastal towns could be devastated, with little time to evacuate. Modeling such events is a challenge, but evidence from past landslides around the world shows why scientists take this risk seriously. Active risk, but the science doesn't stop at risk. Mount Etna's ongoing slide has inspired a global campaign of observation and innovation. Volcanologists from Italy's INGV Observatory in Catania now operate hundreds of seismometers, gas sensors, radar satellites, and ocean-bottom instruments to monitor every pulse, quake, or strain. The volcano endures. Recent research shows flank accelerations sometimes correspond to surface eruptions, seismic swarms, or even heavy rainfall seeping into fractured beds. The challenge is prediction. While eruption warnings can often be given hours, days, or even weeks in advance, gravitational collapse lacks clear precursors. The drift may accelerate gradually, or a single event, a deep earthquake, a rapid magmatic intrusion, or prolonged rainfall could tip the balance in days. The current movement is just a few centimeters a year, reassuringly slow, but a rapid increase might provide only a short window before a collapse. Sicilians live with this risk. For centuries, they have farmed Etna's fertile soil, built cities in its shadow, and celebrated the mountain as both a danger and a blessing. Etna's eruptions have shaped culture, myths, and local pride, always reminding people of the power beneath their feet. With every improvement in observation and early warning, authorities grow more prepared to act if the volcano's drifting slope starts to accelerate. But Mount Etna's story also offers valuable lessons for the world. Many volcanoes, especially those on islands or near coasts, share these gravity-driven risks. The lessons learned in Sicily are now informing monitoring programs from Hawaii's Kilauea to volcanoes in Japan, Indonesia, and the Philippines. International scientists are pooling experience, data, and technology to better understand how and when these giants might move. For now, Etna continues to fascinate. Recent eruptions, such as the dramatic lava fountains and ash clouds of 2025, reminders of the volcano's restless nature. The latest satellite imaging has revealed tiny accelerations in the southeast flank after eruptions, confirming the close link between surface activity and underlying drift. These events become case studies. Each eruption offers new insight into how the mountain's plumbing and flanks interact, and each period of calm allows the most detailed mapping and planning. The scientific community has made huge progress in understanding Etna's nature. A groundbreaking study published in Science Advances confirmed the gravity-driven dynamics, settling a decades-old debate and prompting a comprehensive rethinking of volcanic risk. The realization that gravitational sliding is the dominant threat, just internal magma dynamics, has added urgency to hazard modeling and emergency planning. In the coming decade, more advanced monitoring is poised to give Sicilian communities better protection, and volcanologists new tools to interpret subtle warning signs. For viewers, there is a profound fascination in witnessing how ancient geologic forces, unfolding over centuries and millennia, come together in a single volcano overlooking a vibrant corner of Europe. Mount Etna stands as a living monument to Earth's creative and destructive power, symbol of both continuity and change. If you've watched this far, take a moment to reflect on the resilience of people and the persistence of nature. Etna's story is not just one of impending disaster, but of coexistence, people, culture, and science, thriving alongside a volcano that grows, fractures, and slides. So next time you hear about Mount Etna, whether it's a spectacular eruption, a scientific discovery, or a new earthquake cluster beneath its slopes, steady slide that's unfolding beneath the surface. It's a reminder of both our vulnerability and our strength, and a call to keep watching, learning, and preparing for whatever the Earth may bring next. Thank you for exploring Earth's most dynamic volcanoes with BeyondTube. Like, subscribe, and stay tuned for our next story where we journey into the world's hidden dangers and natural wonders, one eruption at a time.